Hi everyone. This video is on infinite limits. We're still in Unit 1 in Calculus. You can see the objectives here. The first thing we're going to do is briefly review rational functions. We're going to talk about the behavior of a graph at their vertical asymptotes. We're going to talk about limits, just briefly, limits and horizontal asymptotes. We'll cover this later on. Be sure that you're taking 2-column notes, and here we go. So remember that a rational function is the combination of a polynomial divided by a polynomial. So, for instance, you would have a polynomial divided by a polynomial. All right? And so rational functions often have vertical asymptotes, horizontal asymptotes, and sometimes they have holes. And you can see this graph right here has both. It has a horizontal asymptote at y equals 1. It has a vertical at x equals 1. And then it also has a hole in the graph here at -1. Another reminder that the behavior at this vertical graph, you can see as x approaches the vertical asymptote from the left, the y values are going to positive infinity, increasing without bound. And as we come at it from the right, it's decreasing without bound. So obviously there's a discontinuity in the graph. This is a non-removable, and then the behavior shows opposite on either side of it. So there is no limit. It does not exist, no limit. The horizontal, you can see as x approaches infinity, positive infinity, you can see that the behavior of the graph is getting really close to the asymptote y equals 1. And the same as x approaches negative infinity. Remember that a hole is a removable discontinuity. So once again, here's graphically and then a table numerically. We're looking at the behavior of the graph at the vertical asymptote. I know that there's a vertical asymptote because there is nothing that is a form of 1, so there's no hole. And then I also know that if I put 2 into the denominator, then I would get 0. So I would be dividing by 0. So I know there's a vertical asymptote here. Now, the behavior, there is no limit, right? Except that the limit as it comes from the left and the limit from the right are both going in the same direction. So you would say that the limit of this is negative infinity. The limit technically does not exist, but that's what it looks like here. Do you see how these values, as it gets closer here, this is getting negative to negative. The other thing to remember here is there's a horizontal asymptote at y equals 0. So what you're noticing then as you put in these values, you're looking to see what the y values are as they get close to this vertical asymptote. So this is a summary page. So when I look at your notes, I'm really going to expect this to be here. So you may have to stop the video, you may have to take a second and write some of these things down. And as you're doing that, let me just point out some of the highlights on this page. Okay? It says that limits, there are 2 types of limits involving infinity. If it's written in this form, where the x approaches positive infinity or negative infinity, this is the notation that refers to horizontal asymptotes, ones that go this direction. Infinite limits also can take the form of something that looks like this. As x approaches a value a, it can approach positive infinity or negative infinity. Infinite limits in this form are vertical asymptotes, the behavior of vertical asymptotes. It approaches a number, it approaches the asymptote from the right and the left. Okay, so a limit statement, here's a summary here, the limit statement such as x approaches c positive infinity means that the function f is increasing without bound or going in the positive infinity direction as x approaches that asymptote from either side. Okay, and so here that just means it's decreasing without bound as it approaches it from either side. So what that looks like is this, where they're going in the same direction, or this, where they're going in the opposite direction. So stop it as much as you need to. We're going to talk about the horizontal again in 3.5. We've been talking about it and it makes a lot of sense, but we're going to talk about it again later on after we've covered derivatives. So this is a huge, another important point. It's in a box. If this were in the chapter, I would say this is in the box. This is important information. Plus it says the word important, whatever. So it says these statements that have infinity in them, like the ones that are right here, where you have x approaches a is positive, x approaches a negative. It does not mean that the limit exists. It does not mean the limit exists. These mean that the limit does not exist, but and why they fail to exist. Because they go to infinity, they do not exist. Because they go to positive infinity, they do not exist. So they're just describing the behavior of the function at the asymptote. That's what positive and negative, if you have that for the limit, it is just describing behavior. It does not mean that the limit exists. So that's real important. Be sure you have that in your notes. Okay, so here we are at an example. Let's do a real-life example. We know this is a rational function. We know it's a rational function because it has a polynomial in the numerator. This is in the numerator and a polynomial in the denominator. And so if we use direct substitution, if we substitute 4 in there, we're going to get negative 4 over 0. So that's indeterminate form. Okay, and there is nothing to factor. There's nothing else to do with that. So let's analyze it in terms of being a rational function. I cannot spell using this. Hold on. Rational, I think I'll just say it. Rational function. All right, so let's talk about, does it have a whole? Well, is there a form of 1? No. So there are no wholes in this rational function. The denominator is x minus 4. I know that means that there is a vertical asymptote at x equals 4. I also know that there is a horizontal asymptote because I analyze the highest power in the numerator is x. The highest power in the denominator is x. And so I would, since they're the same, I would say y equals their coefficient, which is 1 over 1, which is y equals 1. Okay? So that's just analyzing. If I wanted to graph it, I could do a quick sketch. But what I'm looking for is I'm looking for the behavior at the asymptote. We want the behavior at the vertical asymptote. And here are my possibilities. Of course, none of these exist, right? They're not limits. But I could say that on either side it does that. Or the opposite. It would do like this. Or it might be together, although I can tell you by looking at it they won't be together. And the reason I know they won't be together is to be together, the denominator would have to be a perfect square. It would have to be, it would have to look like x minus 4 quantity squared in the denominator. So it's not going, this particular one is not going to look like that. So what I want to know here then is, or what I'm going to know here is that there will be no limit. Why? Well, because if you eliminate this possibility, and these are your only possibilities, then you know that it's going to be different on one side than the other, and there will be no limit. It does not exist. They're not going in the same direction. Now, sometimes problems like this will say things like, find the limit as x approaches 4 from the right or the left. And that you can do. And I'm going to show you on the next one how you can do that with estimating. You can also put it in your calculator and see what it does that way. So here, these are the possibilities for vertical asymptotes. It says the line x equals a is a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. And so it says as it approaches, it's positive infinity, negative infinity, approaching from the right, approaching from the left, or one of those possibilities that we had talked about there. For instance, this one means this, and this one means that, right? They're together, both on the same. This one means that from the right, it's positive infinity, or from the right, it's negative infinity. From the left, I'm having a hard time reading that, but I think it looks like that. So you're talking about, what's happening on either side of the asymptote. So on this is just, once again, a rational function. I know that there are no holes because there's no form of 1. There's nothing to factor, so it's in lowest form. The vertical asymptote is the denominator, so it's going to be at x equals -3. The horizontal asymptote, once again, I have the same, so this is going to be y equals 1. And then it says sketch the graph. So got this graph going on, change colors real quick. I know this is at 1, 2, 3, and 1, right? And I also know that there is an x-intercept at x equals 2. So if I put a 2 in there, that's going to be 2 zeros, so that'll be this. So it's going to look something like this. Okay? So what would be the limit there? Well, the limit, there would be no limit, right, because it's opposite directions. The limit from the left would be positive infinity, and the limit from the right would be negative infinity. Okay, here the example says determine the limit as x approaches 2 from the left of x minus 8 over x squared minus 4. Now once again, this is a rational function, and that's what infinite limits are about. You're looking at asymptotic behavior, and rational functions have asymptotes. So that's why most of the examples, I'm going to do one that has a trig function on the next. But okay, so we're going to factor the denominator. That's going to be x plus 2, x minus 2. Once again, there are no holes, no forms of 1. I'm going to have 2 vertical asymptotes, one at x equals -2 and one at x equals 2. The horizontal asymptote, I have x over x squared, so it's big on bottom, so y equals 0. Right? And I want to know the behavior as x approaches 2 from the left. So as x approaches 2 from the left. All right, so what does that look like? Well, in a table, if I had a table going on here, I know that there's an error at 2, but I know that from the left is 1.999, right? 1.99 and 1.9. And then past it would be this, right? But I don't need the right, but I have it if I needed it, but I do need left. So let's estimate this, because you can put it in your calculator, of course, and you can find it that way, but what if you don't have a calculator? So let's think about this. Let's put in 1.999 into the original problem. I'm not going to know the exact value because I'm not going to take the time for that. But on the top, I would have -8 plus 2, which is a negative number. On the bottom, I would have 1.999, which is a little less than 2 squared, which is a little less than 4, which means that this will also be negative. Well, a negative over a negative is positive. Since my horizontal asymptote is at 0, I know it's going below the x-axis, and so that means that this is going to be the limit as x approaches 2 from the left is going to be positive infinity. And if you graph this thing, this is what it looks like. Got this, right? And then I've got vertical at 2 and -2, and then a horizontal here. And if I graph it, it looks, oh, it's not letting me, hold on. There. And then like this, and then like this. So as you can see, as it approaches, right, from here, it is going to positive infinity. If it's approaching from here, it would be negative infinity. Because it's just one-sided limit, then I actually would say that it is positive infinity. Okay, one more example, because not everything with an asymptote is a rational function. Sometimes it's a trig function. You know that sine and cosine don't have asymptotes, but tangent, cotangent, secant, cosecant all have asymptotes. They all have places where the value does not exist. So we're looking here at the limit as x approaches pi over 6 radians of tangent 3x. Tangent 3x, triple angle, means that it is covering more of the tangent graph in a smaller amount of space. So I just want to remind you that when you're looking at the limit, the first thing that you're going to try possibly is analytically. And so direct substitution. So if I put in, I find I'm looking for the limit as x approaches pi over 6 of the tangent of 3x, 3x. And so if I put tangent, that would just be the tangent of 3 times pi over 6, which would be the tangent of pi over 2. All right? The tangent of pi over 2, remember tangent is sine over cosine, right? And at pi over 2, it would be the point 0, 1. So this is going to be 1 over 0, which is undefined, not, right, indeterminate form. Well, there's nothing else you can do with that, so we're going to estimate. Obviously, here, we also know from our tangent function that that's a vertical asymptote. There is a vertical asymptote at pi over 2. So this is actually asking us, what is the behavior at that vertical asymptote? What is the behavior at that vertical asymptote? Okay? So, if we were graphing this, right, remember that the tangent graph goes through the origin. It's centered on the origin because the tangent of 0 is 0, right? Because this point over here, if we were doing the unit circle, this point over here would be 1, 0, right? Always, so the tangent of 0 is 0 over 1. And remember that tangent goes this way. So guess what this asymptote is? This is pi over 6. This one is negative pi over 6, and it goes like that. And we remember that tangent functions, just like all of them, are periodic, which means they repeat in infinitely both directions. So we can kind of see here, as we're looking at this asymptote right here, we see that from the left, it's going to positive infinity, and from the right, it's going to negative infinity. So the limit as x approaches pi over 6 of 3x, there is no limit. It does not exist. It's not going in the same direction. It's the opposite. I could also say the limit as x approaches pi over 6 from the left, right, from the left is going to be positive infinity, and the limit as x approaches pi over 6 from the right of f of x is negative infinity. And that's why. It's telling why there is no limit, because it's not the same coming from one direction as it is the other. So I've taken a long time on this video, and I know there's a lot to write down here. I think a lot of it is going to be a confirmation of what we've already been talking about a little bit in class. But be sure you have these notes written down and ready, and we'll work some more problems in class, and you can ask questions on anything you don't understand here. So I will see you then.